Let's talk about charting. So I'm Chris Trevino, and I'm a software engineer at Microsoft Research in Silverdale, Washington. I've been with Microsoft Research for a little over a year, and I've been doing JavaScript for about 5 years. Before that, I was working in C++, embedded systems, and Java web services, so I use classes a lot. Please don't kick me out. But it looks like that'll be changing soon. Let me get my mouse back. So to set the context of this talk, I'd like to talk a little bit about my team's work. So we're a newer team at Microsoft Research, and we're made up of researchers and data analysts, back-end developers and front-end developers, and our emphasis is on applying data analytics and machine learning and visual analytic processes to large sets of text data, and then trying to convey insights from that data. So our team builds a lot of interactive visualizations to try to communicate key insights in data and give users kind of the freedom to explore and see what's in there. And a lot of times, our work is as simple as wiring up a Power BI notebook with some ready-to-go pre-made visualizations. Other times, we get to go and make one-off experiments that help us kind of frame our thinking about certain kinds of problems or experiment with different mixes of technologies. And sometimes we get to go and make applications in the web and on mobile using React that deliver a custom experience and tell a very specific story with data. And now this is just to emphasize that for us, data visualization and visual analytics is absolutely essential to what we do. And it's our primary mechanism for understanding nuance in data that's often like hard to discern in its raw textual form, or maybe even like it's impossible to look at. And I would wager that data visualization is important for you too. Maybe it's not something you use all the time. Maybe you don't need something that's new or novel. But we're all UI developers, and it's a problem space we all run into. And usually this takes the form of charting. So when we talk about charts, we're usually talking about a few common types of charts. There's your basic bar charts, line charts, kind of gross pie charts, area charts, and if you're getting like fancy, maybe you want something cool like a box plot or a radar chart. There's a ton of classical charting types, and you're going to find the basics of these pretty much in any library you download. But now and then, you may need to solve a problem that needs a custom visualization. Or maybe just something as simple as you want to take one of these simple base visuals and then make some minor variant on it. And so to kind of illustrate this, I'm going to walk through an example. So let's take a moment to talk about our experience using charting libraries. This section is a little bit unfair, so please bear with me, but I hope it paints a specific picture of a kind of problem people have when they use certain types of charting libraries, or just dealing with high abstractions in general. So let's say we're knee-deep into making our application, and we need to include a chart for a metrics page. Fortunately, it's nothing fancy. We just need to make a bar chart. So we head over to NPM, and we search for something simple that matches our use case. And we find this cool library called Fancy Charts, which is super popular, has a ton of downloads and stars. And so we go and we check the API docs, and it looks pretty decent. It has a clean, upfront interface. We just pass our data in, and charts pop out. So we install this sweet new charting library, and we're stoked. Nothing is going to go wrong today. So now we wire it into our app. We import the bar chart component. We add it into our render function. We send in our data over the props interface. This is so good, it couldn't be easier. And now we have a bar chart. It's thrilling, right? So we finished something today, and it's Friday, so maybe it's time for beer 30. However, our manager has discussed the requirements with the customer, and our fancy bar chart needs just a little bit of work. But it's no big deal. You definitely should not freak out about it. So according to our new requirements, all we need to do is add a mean line to our bar chart component. So we head back to the API docs. Is there a way of adding some new mark to this? Can we add a child? We look at it. No, we can't. Kind of ruins our day. So at this point, we've fallen off the cliff of abstraction. The abstraction we're using is brittle. It's not expressive enough to adapt to subtle changes in our requirements. And at this point, we may be so frustrated that we just eject our charting library entirely and go straight down into dealing with 2D APIs. And maybe that means installing D3, figuring out how to make D3 and React work together. And there's a couple different ways to do that. There's no right way to do that. We call this problem the problem of the missing abstraction. And basically, the problem is this. We want to be able to author our visuals in high-level terms, but we run into these brittle abstractions that force us into low-level rendering. And it feels like there should be something in the middle of these two options. Something more verbose than a chart tag, something higher level than a graphics API, but something that kind of maximizes our productivity and expressivity and minimizes the time it takes to design a new visual and test it out. So let's look at what may fit into this abstraction gap. We're going to look at this from a couple of different angles. In a second, we'll look at academia. But first, let's look at composable charting options in the React community. So one great option is Victory charts. Victory is super popular, has a bunch of great features. And one thing I love about it is that's the only library that has any notion of mobile parity at all that you're going to find. Another great one is React Viz. Their API is pretty flexible and low level. And we've used this in some of our own applications. And finally, there's Recharts, which we actually haven't tried out yet, but it's pretty popular on NPM, and it has a pretty great API and great API docs. But there are some issues that you may run into when you're using these, and I definitely do not want to trash these libraries. And maybe these things aren't really deal breakers for you, but they're just things we've run into. So one thing you'll notice is that to varying degrees, their APIs are kind of taxonomic. So if we're talking about a purely taxonomic API, that'd be one that reflects a fixed series of chart types. Like you could have a bar chart, line chart, pie chart. You might even be able to compose them and do some creative things, but it's kind of like using pre-made sentences to express ourselves instead of words. So let's just peek into the APIs of these for a little bit. Victory's top-level API is taxonomic, but if you dig just a little deeper into the documentation, they do provide a couple of levels of lower-level charting elements, and they do a pretty good job of glissading between abstraction levels. Here's the top-level Recharts API, which has taxonomic chart containers. And what that means is that your top-level chart is something like a bar chart or a line chart, and it limits what legal children your chart's allowed to have, which can kind of feel arbitrarily restrictive. Finally, there's the React Viz API, which has a series of a set of shape series components, which kind of makes this the least taxonomical API here, but it is the only abstraction level. So one-off elements, custom things in here, are going to require some manual work, probably in SVG, which brings us to our next concern, and that is we're always kind of coupled to a specific rendering technology. So in Victory, this is kind of how we add low-level elements to our chart. So in this piece of code, we have an area chart that's rendered adjacent to a circle, and it's done by thunking down to raw SVG, which gives us nice flexibility. We can do absolutely wild things with SVG, but the abstraction is a little leaky, and it locks us into SVG. In React Viz, it means that for each component type we're interested in, there's a canvas version and an SVG version. So if we do any of those one-off SVG tricks, it's going to be hard to pivot between these two different rendering technologies. In any of these libraries, and honestly in every charting library I've ever used, it means that we are solidly coupled to the DOM. And this is one of the reasons why getting parity on React Native is such a giant pain. Only Victory has any kind of mobile parity at all, and you have to install a separate library to get it, which means that some of these raw SVG tricks that we're using aren't necessarily going to port well over there. So let's back up for a second and look at this problem from more of a theoretical perspective. One idea that we've heard about being, that we're adjacent to people who are well-read visualization researchers is that of the grammar of graphics. So this is kind of an exciting idea that we found satisfies a lot of our expressivity wants. It's pretty common to find in visualization and research circles, but it doesn't seem to be super well known to practitioners. So let's talk about the theory a little bit. So the idea comes from a book that was published in 1999 titled The Grammar of Graphics by Leland Wilkinson, who's a well-known visualization researcher and like a VP of Tableau software. And these ideas have a handful of explicit implementations in various programming ecosystems such as ggplot, ggplot2, Altair. And so the grammar graphics envisions a system of object-oriented charting elements that operate together to form charts. And it's called a grammar because these elements are analogous to using words in sentences to express our meaning. You can combine them in expressive ways, but there's also kind of rules on how you use them. And this was diametrically opposed to charting technologies at the time, which were taxonomic in nature. So a major emphasis of the grammar graphics is to eschew taxonomies entirely in favor of more expressible kind of Lego pieces. These elements consist of the basic pieces of charts we're all familiar with. So we got shapes to draw, scales that map our data to view dimensions, coordinate systems for you to draw your shapes into, guide components that help users know what you're looking at, and data transformation components for things like aggregation, statistics, layout computation. So say as an example, we have a rectangle component. We want to encode an instance of it into a Cartesian space in our chart. Our rectangle will encode some properties based on the specific piece of data it's bound to, and each of these properties are going to have a scale applied to it. So in this case, you've got an x and y start position, a width and height, and the color of this thing. Now this is basically how we think about components working, right? We parameterize our elements in our apps that encapsulate some behavior of some kind. They may or may not interact with each other, make some functional result in the end, and then we kind of compose them in our applications in an expressive way to solve a problem for ourselves. So in Wilkinson's book, the grammar graphics is described by a specification language, and then a chart's created by working through a workflow. And the main phases of creating charts using the grammar graphics are described as, first, we specify a scene using chart element components, the stuff we just talked about. And then we assemble an abstract scene graph, which means taking our data sources and walking them through our specification and emitting something that looks like the abstract notion of a chart. And then lastly, we render out to that scene graph to whatever output our system supports. Now, if you squint just a little bit, this looks a lot like the phases of how a compiler works. And the abstract scene graph plays the same role as the abstract syntax tree does for compilers. So in compilers, you have a front end that turns your program into this abstract syntax tree, and then you have a back end that turns that abstract syntax tree into bits that your computer reads. And this architecture allows compiler authors to be able to switch languages or runtime environments fairly easily without needing to redesign a whole system from scratch. So it's kind of important that this scene graph that we're talking about is abstract, because it should give us the ability to pivot rendering technologies or give us flexibility in how we author these scenes. So you could consider SVG or DOM types of scene graph specifications, but they're like coupled to technology and they're coupled to the browser. So this is a really cool idea. It fits nicely with our component-based way of thinking. So what are some options for implementations of this? If you're in Python or R, you've got ggplot and Altair, which are widely used. But we're JavaScript developers, and being JavaScript people, the 800-pound gorilla in the room, the main implementation of note is called Vega. So Vega is a project made by University of Washington's Interactive Data Lab. And our first exposure to this, and to the grammar graphics in general, was when Dominic Moritz, who's a PhD student out of UW, came and gave a talk on our campus about Vega Lite, which is a lighter weight version of Vega. So let's look into Vega. Let's see how you'd write a bar chart. Oh, that should have been at the top. So in both Vega and Vega Lite, you author visuals using static JSON definitions. So Vega is basically a superstructured D3 with kind of a notion of scene nodes. So to start, we set our chart options, are we using SVG or Canvas, the background color, the dimensions of the thing. Then we wire in our data tables. Each table has a name, and it can either be like a remote URL or a static array of objects. For event handling, Vega has what they call an internal signaling system. So in Vega, signals are named variables that charts can bind to and then update in response to interaction. You can think of it as kind of like an embedded declarative redux inside of these. Next, we define our scales. It's how we map our data dimensions to UI dimensions, such as width, height, color. Each scale here is a named object, so we can reference it later. Then we'll define our axis components, oriented to the edges of our view space. These don't actually land in the scene graph themselves, but they're kind of a type of component that it's kind of higher order, and then we'll spit out lower level things into the scene graph. And then finally, we have our visual components. So we're making a bar chart. We need rectangles. We can bind these to a data table, in which case, like every row in the data table will emit an instance of this thing. And the attributes can be bound to either data scale combinations or to static values. And now we have a bar chart in Vega. So there's some good component-based thinking going on here, and it's incredibly expressive and can describe a broad array of charts. And they have they have a ton of great examples on their website. But a declarative JSON-based API is kind of a pain to work with. So you don't have great debugging schemes, and it can be difficult to reason about the structure of a chart. And as you're making more and more complex visuals, that problem is only exacerbated. So we really like the ideas here, but we prefer the ergonomics of the component-based charting libraries we were looking at before. So our question since first learning about Vega and trying to integrate into our own applications has been, what if you were to have access to Vega's abstraction level, but you expressed it with a component-based API instead? And so, being incredibly naive and full of hubris, we decided to make our own library. And we're calling it Chart Parts. And it's our love letter to Vega, and I hope they're not too mad. This project is fairly experimental. It's still in its early stages. And it's experimental for my team because it's one of the more ambitious open source things we've done. So let's look at the top level React API of this thing. So we provide a series of charting components based on the Vega API. So the types of things you can have are scales, view marks, and guides. There's a bunch of scale components, and these all basically thunk down to D3. And we implement the most of the mark types we use most from Vega. There's basic shapes such as line, wedges, rectangles, text, that kinds of thing. There's some data series marks for doing things like line and area charts. And then there's a special group mark that lets us subdivide our charting area and acts as the scene node. This basically acts, it lets us pull off combined charting and data faceting type things. There's an access guide type. And then there's some components that are kind of in the to-do bucket, like legends, component-based data flow, animation, images, and anything geospatial. So let's look briefly into the architecture of this thing. So we started out by using Vega's scene graph, which is a plain JavaScript object that describes a chart at a low level. Using these scene graph objects, we built a transform pipeline to turn these scenes into pseudo SVG and then to React Virtual DOM. And this piece of the library came up really quickly. We decided to lean into React's render and reconciliation algorithm, and we kind of sidestepped a lot of time-consuming work in dealing, deep in the guts of DOM manipulation and keeping the DOM in sync with scene graph changes. So this may change in the future, especially as we start looking at renders like Pixie or something, but it was super encouraging to see this part of it happen very quickly. The next piece of the library, which took a bit of time, was working on the specification and scene graph generation pieces. So we have a generic scene builder fluent API that's not framework dependent, and that's what you use to describe your scenes. And then on top of that, we have a React renderless API that uses the scene builder API, so this feels nice and home when you're in React. And if you're unfamiliar with renderless components, I'm sure everyone here knows what they are, but they're components that render out null, but have interact with APIs as side effects as they mount into the virtual DOM. So one interesting thing about this architecture as a whole is that we're only in React at the very beginning and end of this process. So if we ever want to target another framework for some stupid reason or another rendering environment, we don't have to swap out the whole library. So let's make a bar chart with chart parts. Go back up here. So first we'll import our charting components. Then we'll pick a renderer. In this case, we'll render out to an SVG. Then we'll write out the top level chart. And here's where we set the dimensions, inject our data tables, select a renderer. Next, we define some scale components. Each of these scale components can be described at every scene node. So each scale has a name, and we can bind a domain of these things to a column of our data, and then the range to a dimension of the view it's currently in. The available space these things use will automatically be pruned if you have things like axes at the same scene node. Then we add our axis components, and at a minimum, these need to be anchored to an edge of the view space and bound to a scale. And then finally, we'll add our graphical marks. So with these, we can bind our data table to a data set, and then for each row in that table, we'll emit a rectangle into our scene graph. If we're not bound to a table, this will only just be a singleton instance. And then we encode attributes to the marks. So with attribute encoding, this can either be a static value, or we can use an encoding function. So when you look at the code here, it may look kind of weird, but the encoding functions are kind of special here. They're functions that have a single parameter, and it's a context object, and it has the named data tables, scales that are currently in scope, the current view dimensions, the current row being bound called D, and the index that appears out in your table called index. Then finally, we can go and add event handlers. Being application developers, we're kind of used to managing our own state with things like Redux, so we kind of opted out of the declarative signal system in favor of just having native events here and deciding what to do with them ourselves. And here's our bar chart. Woo! I know, it's thrilling. So I'd like to walk through just a few more examples to highlight some things about chart parts I think are pretty cool. So first, let's talk about accessibility. Accessibility is extremely important to Microsoft, and like it should be for all of us. Non-sighted users tend to be underserved, like in general, but it's especially true in data viz. So one of the questions we asked ourselves was how we can make, how accessible could we make these things? And so, after looking into it, we did some research. SVG supports ARIA tags, and so we extended the Vega scene graph model so that we could pack our SVGs with ARIA tags. And by using that, we can deliver interpretable charts to non-sighted users. And so this is definitely an area that needs feedback. So if you use a screen reader, we would love to get some feedback on this. And right now, it only works with our web SVG renderer, but here's how it looks. So first off, we can add an ARIA description to the top level of the chart, and that would give a screen reader user a high-level description of what it is before they decide to dive into details on it. Then we can encode tab indexes, so their screen reader will stop at marks as they walk through it. And then finally, we can add ARIA tags to individual elements, and we can encode these like any other parameter we have to let the ARIA tags reflect the data that they're bound to. And so here we have an accessible one, and we'll try this.
Spoken feedback is ready. Window, the missing category E value is 28. Category B value is 55. Category C value is 43.
Woo.
Bar chart, an example bar chart image.
All right.
Window extension
Turn that off.
tab.
Sorry. So I've mentioned that we use renderless components, and one nice side effect is that we can use functional components to kind of organize our API interactions, which should make, if you have a well-made chart, it should be easier to understand than a giant static JSON file. So in some component libraries, and this is of any type, not just charts, you'll see some boilerplate work to ensure that parents only have valid children types, and that kind of precludes us from being able to have our own arbitrary organizational structure. So please don't do that. But let's look at something slightly more complex than a bar chart. So this is a population pyramid chart. And it's basically like two bar charts that are mirrored and faceted, each reflecting different facets of the population. So this is the population of men and women broken out by age, and then we can go and drag the year around and modulate what year it is, if I can grab onto that. Yeah. So this seems like it could share some structure internally, so let's look under the hood. So at the top level chart, we kind of get a bird's eye view of the overall structure of everything, right? We have scale definitions, we have that age label column, and then the different facets of the population here. And if we zoom into this, we can see the scale specifications, that age column, and the gender per year components, which then share an underlying low-level definition. So, I mean, you're all JavaScript developers. These are all familiar techniques that we use to manage complexity, to reduce duplication, but it's one of the benefits we get from using JavaScript instead of JSON. So let's look at another example. So our library uses an abstract scene graph, which means we can change the target rendering technology to whatever we want. So right now, our library is just emitting React Virtual DOM for SVG, and we can just as easily emit React Native Virtual DOM. So now it's possible to share our charting definitions between our web apps and our mobile apps. And so how do we do that? The first thing we do is swap out the render. We pick the React Native SVG renderer, plug it into the chart, and then if it's responsive to events at all, we have to handle touch events instead of click events. And that's it. So let's take a look at it. Here's that same population pyramid running in React Native. Woo. Get back here. So the flexibility afforded to us by renderless components also allows us to compose and augment our charts in a kind of a very fluid way. So let's try to add that mainline component we started out the talk with. First, we'll define a mainline component. Here, the rule type will draw out a single instance of a line. You'll notice it's not bound to a data table, so there's a singleton instance. The x parameters we're going to bind to the view dimensions, and the y value will be the computed mean in the data. And then we render this into our chart, so we just have to extend our chart definition to allow children. And if we added like a more complex scene, we can use render props to customize where things get injected to, but this will work just as well for this case. And now we have the basic elements that we want, and we can compose them pretty easily. And now we're dealing with exactly the kind of abstraction level we want to, right? We have meaningful components for us made out of low-level primitives, and we can compose them in arbitrary ways. And then we have our mainline component. And that means that we've solved our problem, and Beer 30 is back on. So the grammar graphics is an idea that my team believes in, and we hope it can kind of reach a broader, more mainstream audience. And ChartPart solves some very specific problems for our team. We plan to continue developing this tool to take that experiment as far as we can to make it solve our problems, but we came here because we want to welcome your feedback, your contribution, your perspectives, because we want to make this a great tool for you as well. And we hope it becomes a great tool that's valuable in the React community. So check us out on GitHub. Check me out on Twitter at the worst Twitter handle ever. Or chat me up during a break. Thank you so much.